So a truism is no matter how the flux changes, how that change is produced, if you have a non-zero dφ/dt, an epsilon will be generated, and epsilon and the induced current will oppose this change. We have two statements here. We have the statement that we will get an EMF, and then the other is that the polarity of epsilon and the corresponding induced current will oppose the change. So let's go back to our coil and look at the derivation of the value of epsilon as we're doing this. So remember, we have a constant B, and we're pulling the loop out of, or pushing a loop into the B field, either one. In this case, we're pulling out. So what happens to the area inside the B field? So that's A inside. That corresponds to this rectangle ABCD that we've talked about before. That's what's changing with time. So the A inside, where we have non-zero B, will be equal to h times the distance x, which is L minus V times t. L is the total distance here. X is the distance where we're inside the field. And so if we subtract x from L and then use x equal Vt, then we come up with this quantity here. Well, going back to our discussion of phi is changing with time because A is changing with time. So B times A is the flux, and so if we put in our A inside equals to h times L minus Vt, then we can see that when we form the derivative of phi, we end up with epsilon equal to minus BHV. So one more time, we take the derivative of phi, which is this quantity here. This is a constant, and then we have minus V times T, so BH times V. And of course, when we take the derivative, we just drop the T, and that's how we get the epsilon. We're going to do this again later, so please try to remember that. We've come up with epsilon, and we've already come up with the polarity. So what we're talking about then is the EMF across these two wires, which will then generate the current through the resistor. Let's take another example, the one we had before, where we produce B by movement of the magnet. So we know that B is increasing to the left, and so we predict the direction of epsilon and I induced. And so again, we have epsilon being the derivative of phi with respect to t, and that's going to be minus the derivative of the area of the coil times B. But the area of the coil is a constant, so we can bring that outside, and so we just have the derivative of B of t with respect to t. I would just want to remind you that if we have n turns in the coil, we will multiply the above by capital N because the flux is n times BA. So here's our result then. Our epsilon is equal to n times A times the derivative of B with respect to time. So the good news is we have a starting point for an equation. The bad news is we really don't know B of t, even though we know that it's changing because of the movement of the magnet. It's changing inside the coil. So we really can't quantify the change in flux or the epsilon. So we'll leave it there. So a third way to generate an EMF would be to move a coil. So now we're moving the coil through an inhomogeneous B field. To make this interesting, we want the orientation of the coil to be such that B dot dA is unequal to 0. So let's take the simple case where we have B changing in the x direction only, and it has a very simple form. It just looks like a B field which is increasing with x. We'll make B0 positive. And we'll let the coil be oriented so the normal to A is such that A is equal to x hat. So this is along the x-axis. We'll let V just be V0. This should be a times the x hat normal vector with V0 positive. So we've really simplified this considerably. But the point is that B depends on the x. It's changing as we move the coil. It's going to start in a weak field and move into a stronger field. The orientation of the coil, which is given by this vector here, is right parallel with the V and with the changing B field. So what happens then? We have a B in this direction. How is delta B changing? Well, it's increasing as we move. So it has the direction that I show here. Do you get that? So if we have B increasing in this direction as we move, the delta B will be in this direction here. So immediately we can say that the induced B in the coil will have to be opposing this change. That's Lenz's law right here. So here we go. Here's the flux. The flux is B times A with the dot product. Because these are parallel, we have x hat and x hat here, and we have Bx times A. Here's the final value of the flux, and notice that flux is always a scalar. So here's our reminder in order to get the polarity of the EMF. And so we take our flux and take the derivative. These are constants, so they come outside. And so the only thing we're differentiating is x, and dx dt is the velocity. So we have minus B0A times V. And the polarity, we'll have to use Lenz's law. Just a reminder, if we have n turns in the coil, we have to multiply by n, so I put that into the expression. Here's epsilon. We've already determined that we have to take the derivative. Here it is again. For n turns, we have minus B0 AN times V. Now we come back to our coil here, and we want to produce a B field which is in this direction. So use the right-hand rule and wrap around the coil accordingly. So the current here has to be flowing in this direction, and the current here has to be flowing in this direction. So that means that the current through the resistor will be as I show here, which means this is a plus and this is a minus. That's all Lenz's law. We've got the direction of the induced current, and we have the polarity of the EMF. If we were to take more complex B fields, for example that it's changing in 2 or 3 dimensions, and we have a complicated V, one that might depend on time, one might depend on the position, then we're really going to have a hard time. This simple case, of course, we can do right away. Here's another way that motion can create an EMF. Actually, we grouped a bunch. We can change the size, shape, or the orientation of the loop with respect to the B field. It always is in the B field. The entire loop is in the B field. In order to get this change, all of them require movement. In the case of size, you're changing, for example, the area enclosed by the loop. The shape, you would probably be changing the area, and of course the orientation. And we're going to consider that particular case. So let's suppose we have a coil. So in this case, it's shown here as a rectangle. The B field is up in this diagram, and the width of the coil is little l, and this width is W. What we're changing then is we're going to rotate this coil and look at the change in the flux. I show it on the side here. So we're taking the 2 wires A, B, and DC, which are looking on end of those, and we're rotating them around this point right here. So around this axis right here. The angle theta is the angle between the normal to the coil and the magnetic field. So let's look at the flux. We're going to assume that B is constant, and we know that flux is the integral of B dot ds over the surface S. B is a constant, so we can bring that outside, so it's the dot product of the integral over ds. Well, the dot product gives us a theta dependence. The integral over ds in terms of magnitude just gives us S. The flux depends on the angle theta, as you see here. And just to remind you that if we looked at B perpendicular to S, we would be at theta, and the other angle that corresponds to that is 3 pi over 2. Then what we have is this coil here oriented right along the B field. So there is no flux flowing through the coil because B and the orientation here are parallel. And that will happen at theta equal pi over 2, and it will also happen over here at 3 pi over 2. So in that case we have phi equals 0. If you take the parallel case, so where theta equals 0 or theta equals pi, then you have your maximum flux. You can see here that if you orient the coil in this direction like this, then all of your B would be flowing parallel to the A vector, and that's going to give you the maximum. Basically what you're looking at is the cosine of theta in terms of its effect on the flux. And remember that theta is the angle between B and S. So if we look at the quantity theta, let's spin this at a constant rate. So we'd have an angular frequency omega times time would be equal to theta. And we'll set that equal to a constant. So if we take our d phi dt, then our EMF will be minus d dt of the flux, which is right here. Now it has a time dependence. If you take the derivative of the cosine omega t, you get this expression here. This minus sign cancels this one, and we're ending up with this quantity here for the EMF. And we're talking now about the voltage across these two wires. If we plot that, as you imagine, it's a sine wave, and the point is that here you have no alignment so that your flux is zero. Here you have the maximum flux because you're perpendicular. This gives you the EMF as a function of time. In this case, I just took omega t. Well, the question is to close or not to close. Do we still get an EMF? And what I'm talking about is what's sitting between this wire and this wire. In this case, we have a closed circuit, and we know that an EMF occurs. It ended up putting current through R when we have R closing the loop. So we're fine there. However, if we have an open loop, so we have an open circuit, do we still get an EMF? The answer is yes, because what happens is charge separates between these two wires, and the charge will separate until we have a charge separation giving us an E field and a potential difference due to the force on the charge, and when those become equal, you'll get an EMF across there. An EMF is still generated with an open circuit. And we could go back to our coil. We could leave this open, and this EMF would still look like this. There'd be no current because you have not closed the loop. But I just wanted to make sure you understand that we don't have to have a closed circuit in order to generate an EMF. Perhaps an analogy would be a battery. So you have a battery here, and you have the electrodes. If you leave it open, so you don't put a resistor across here, you have a voltage. And the battery is generating that voltage via the EMF. If you now put a resistor across here, like we've done before, the battery can maintain the current. You still have the EMF between the poles. Here's a simple example of a motional emf problem. Let's suppose we have this rectangular loop. The width of this is L. And the loop itself has mass. So the mass is m, and the resistance of the loop is R. We're going to release it while it's in the magnetic field. Gravity will pull it down. And so what we'd like to do is get the velocity of this loop versus time. And we'll start at rest. So we'll let v equals 0 at t equals 0. If x is the distance fallen, then v is the derivative. And we've already done this by pulling on the loop. We were able to get the flux change. If we take this similar problem, we can write down the change in flux with velocity. And if you remember, it's just bh times the velocity. Here we've changed h to L, so that's why I have it written here. Repeating that then, this is the change in flux, and so now we want the induced EMF. So all it does is changes the sign, and so now we have positive values here. Since we use it, we're going to need Lenz's law anyway. It's sort of an unnecessary step. Here's the induced current, so it's epsilon over R, so that would be BLV over R. The force due to the induced current, the force on the coil, if you remember, if you have a loop as we have here, then B times I times L is the force that's induced by that current. Substituting in our current, which is right here, so here's our current, then we can expand that and we end up with BL squared V over R. This is a drag force. The force causing the motion, gravity, will be opposed by the F induced. We can go back to a conservation of energy argument to see that that's going to happen. The other way is just simply to use Lenz's law to get the current direction and see that that's going to produce a force in the upward direction. We're going to put this into Newton's second law. So here's F equals ma. we have the force of gravity minus the F induced. We've already determined that, so that's right here. So we have mg minus the force induced. So I'm going to just simplify this. Let's let alpha be this combination of constants. We can separate this equation. So here's the right hand side. Separate it and we get dv over g minus alpha v, and then of course the dt comes over, and so we have dt on this side. We can integrate both sides, and so I've just shown the integrals here and then what the results are. So this term here gives a log dependence, so we have minus 1 over alpha times the log of g minus alpha v, and of course the right hand side is simple, it's just equal to t. This is an equation we can solve for v, and so the time dependence of velocity is g over alpha times 1 minus exponential minus alpha t. Putting in our alpha, here's v of t, and I've just left it as is. We can quickly put the r above here, and then this is the term that has the exponential in it. If we simplify that, here's the expression that we just wrote down, and so that's the one we'll use. Here's a plot of that function. It's a rising exponential-like behavior. You'll notice that it flattens out here. So as we go to longer and longer times, it looks like it's coming to a terminal velocity. And in fact, if we take our expression, our velocity, and just take the limit of that as t approaches infinity, this is the value of the terminal velocity that we would get. You'll notice that if you have a large r, that's going to take longer. It's going to have a higher terminal velocity. So in other words, if that were infinity, this would just jump up to the terminal velocity very rapidly. If you have a large B field, it's going to take longer, and if the coil is wider, it will take longer. Down here what I've done is just put in some values for aluminum loop. If you look at the mass in terms of the mass density of aluminum times the volume, that would be equal to this expression here. The volume is 4L times A. A is the cross-sectional area of the loop. So here's our resistance in terms of L and the A and the resistivity of the aluminum. If we put that in for V terminal, then it's a little messy, but if you grind on that, you'll find that you get a constant times the mass density and the resistivity of the aluminum. So it doesn't depend on the size of the coil. And then this is divided by B squared. So putting in the numbers for aluminum, we come up with the terminal velocity to be quite slow, 0.012 meters per second. So next time we're going to address Faraday's law, which is an extension of what we've found here in terms of motional EMFs.